But yes, now we're on 10:30 on the dot. So welcome back for our next talk today. Is from Sonali Kapuhennayaka from Sri Lanka at the University of Paradenia. And she'll be speaking to us today about the anti-magic labeling in graph theory. So Sonali, feel free to take it away.
Yeah, good morning. So the purpose of my presentation is to talk about the anti-magic labeling. First, we will get a rough idea about the presentation. Here we have found some alternative methods to label three types of graphs using anti-magic labeling. Those are wheel graph, pendant graph, and a new graph called marigold graph. In the introduction, we'll discuss about those graphs, and then we'll apply the labeling method for those graphs, and we'll get a result. After that, we'll conclude those things. So first, we'll go through the introduction. And if we look at the anti-magic labeling, it was introduced by Hartswell and Rangel in 1989. Actually, the anti-magic labeling of a graph G with M edges and N vertices is a bijection from the set of edges to the set of integers 1 to M, and such that all the N vertex summations are pairwise distinct. Next, we'll move on to the anti-magic like labeling method. This new labeling method is also similar to the anti-magic labeling, but the main difference is that this labeling is an injection labeling method, while the anti-magic labeling is a bijection method. So as I said earlier, we have applied these labeling methods for wheel graph, pendant graph, and marigold graph. So if you look at the wheel graph, as you know, wheel graph of order n is a graph that contains a cycle of length n-1, and for which every graph vertex in the cycle is connected to one other graph vertex, which is known as the hub. The edges of a wheel graph, which connects to the hub, are called spokes. Here you can see a wheel graph of order n. Then before we define the pendant graph, let's see what is the corona of two graphs. So the corona of graph G1 and G2 is the graph obtained by taking one copy of G1, which has P1 vertices, and P1 copies of G2, and then joining the ith vertex of G1 by an edge to every vertex in the ith copy of G2. Now we can define the pendant graph as the corona of the form C1 and K1, and the following graph is a pendant graph of order n. Finally, we have created a new graph which is similar to the shape of a marigold flower. Therefore, we named it as marigold graph, and marigold graph is created using n number of copies of full binary trees of height k, and each tree is attached to a common vertex, and all the vertices other than that middle vertex belong to the same level or in one circle. And in this graph, one copy is considered as one petal. So a marigold graph with n number of copies of full binary trees of height k is denoted by m n k. The following marigold graph is generated using 5 copies of full binary trees with height 2. That is, there are 5 petals in the graph, and the height is measured from the first circle starting with 0. That means in this graph, there are 3 concentric circles. Now we'll move on to the methodology. First, we label the wheel graph according to the anti-magic labeling using the concept of anti-magic labeling of path graph. Therefore, we represent the vertices in outer cycle as a path graph and join the first vertex and the last vertex by an edge. Then spokes of the wheel graph can be represented by adding one edge to each vertex. Now, by using this theorem and the concept of anti-magic labeling, we try to label the edges of this one. First, we label this bottom edge as 1, and then label the edge in the right-hand side as 2, and move on to the left edge and label it as 3, and continue that pattern. Since here we consider a wheel graph with even number of vertices, outer cycle has n-1 edges. Then start to label the spokes from n according to the previous pattern. Next, if you find the vertex sum of the wheel graph, those will be taken these values when n is even. Next, here we label the wheel graph when n is odd. The labeling pattern is similar to the previous one. But in this side, we can see that the vertex summations will take different patterns compared with the even wheel graph. Next, we label the pendant graph according to the concept of the antimagic labeling of path graph. Here, the method is similar to the wheel graph, but we represent the pendant vertices by adding one edge to each vertex. In the next slide, you can see the edge labeling of pendant graph when n is even, and this is the edge labeling when n is odd. Then when we move on to the next slide, it is given that a summary of the edge labeling of pendant graph when n is odd and even. In the next slide, it shows how to apply the antimagic light labeling method for the marigold graph. We know that the marigold graph is created using full binary trees. Therefore, here we use the concept of antimagic labeling of full binary trees. When we consider the edges at the bottom level, we just put the number of the position of that edge. And when we consider the edges at the other levels, that means except the bottom row, we define a function to label those edges as 2 to the power k plus 2 to the power k minus 1 up to 2 to the power l plus 1 and plus I. This I is the position of the edge at the lth level. From this figure, we can see an antimagic oriented with height 2. Now, as you can see, the edges are labeled in a monotonically increasing sequence. So the vertex labeling is also an increasing sequence. Therefore, we can say that all vertex sums are pairwise distinct. Next, to label the other copies of the graph, first we should take the summation of edges in the first petal as J1 and label the edges in the second copy starting with J1 plus 1 and continue as a monotonically increasing sequence and so on. To label the nth copy, first take the summation of the edges in the previous tree as Jn minus 1. Then label the edges in the nth copy as an increasing sequence starting from Jn minus 1 plus 1. Likewise, take the summation of the nth copy as Jn. Next, to label the edges which are connected all the copies to the middle vertex, we should start the labeling from the edge which connects the first copy to the middle vertex and as a monotonically increasing sequence starting from Jn plus 1. Finally, find the vertex summations for every vertices as usual. Next, we can see that since the edges are in an increasing sequence, all the vertices in n copies and the middle vertex graph is also increasing. Therefore, we can say that all the vertices of marigold graph have distinct values. Now, we'll move on to the results that we have obtained. Now, remember in the method we labeled the wheel graph, we were able to find general equation for vertex sums. Here you can see the general equations when n is even, and the next slide shows the general equations for vertex sums when n is odd. For both cases, we have obtained 5 equations. Then we prove these vertex sums are distinct using contradiction method. For that, we assume each vertex sums are equal to each other and then get a contradiction. And now we have considered each pair of vertex values in both cases. And since every time we get a contradiction, therefore we can say that no 2 vertex sums are equal. Again, for the pendant graph, we just need 3 general equations for vertex sums. And these are the general equations when n is odd. And these are when n is even. Likewise, the wheel graph, here also we use the contradiction method to prove the vertex sums of pendant graph are distinct. And for each 7 cases, we got a contradiction. Therefore, we can say that no 2 vertex sums are equal. Next, the following figure is the resulted marigold graph when the antimagic light labeling method is applied. In the first copy, we label the edges according to the antimagic labeling, and we get the summation of the first copy as 21. Therefore, we'll start to label the second copy with 22 and a monotonic increasing sequence. And finally, we get the summation of the 5th copy as 32,655 Therefore, we start to label the edges which are connected to the middle vertex from 32,656 and started it with the edge that connects the first copy to the middle vertex. Finally, we conclude the results that we have obtained. For wheel graph, we use the anti-magic labeling method of path graph, and then we proved that each vertex sums are pairwise distinct. And also, we can conclude that the middle vertex of the wheel graph take the highest vertex value. And using that, we proved that the pendant graphs are also anti-magic by contradiction method. Finally, we define a new graph called marigold graph, and then we apply the anti-magic like labeling method for the marigold graph using the anti-magic labeling concept of full binary trees. And finally, these are my references. Thank you.
Awesome. Thank you very much for that talk, Sonali. Are there any questions? So a question that I had with the result for the wheel graph. So you had a theorem saying that if the path has an anti-magic labeling, then the wheel graph has an anti-magic labeling. Now, in terms of obtaining like a wheel graph from a path is you start off with the graph and you basically add a dominant vertex for it. And so I was wondering if the results presented can be generalized in that direction in terms of if you have a graph that has an anti-magic labeling, does it apply that the graph obtained by adding a dominant vertex, does that have an anti-magic labeling? And so could the techniques presented here be used to show that?
This one?
Yeah, so just thinking in terms of like in generalizing it, could some of the strategies be used, like if we assume one graph has an anti-magic labeling, then adding a dominant vertex gives another graph with anti-magic labeling, or at least are you aware of techniques that might be able to use to show that those type of results?
Hello?
Yes.
Yeah, can you hear me?
Yes. But yeah, all good if you're not too sure about that possible generalization. Jody also put a message in the chat regarding the marigold graphs, and if you could provide a bit more of an explanation about those graphs.
Yeah, sure. So here we introduced this marigold graph, and this graph is created using n number of copies of full binary trees of height k, and in this graph one copy is considered as one petal. So here is an example of a marigold graph. In this graph is generated using 5 copies of full binary trees, and each full binary tree is in height 2. That is, there are 3 concentric circles. So we define this graph as M52.
Cool. Thank you very much for that. Another round of applause for our speaker today.